Okay, welcome everyone to High Performance Computing, Advanced Scientific Computing. The topic of today's lecture is a short introduction to Unix and SSH, and it's a practical lecture, our first practical lecture in the course, which means we will not only have slides, I will also demonstrate some aspects of Unix and also some aspects of SSH. Both are very important for high performance computing, and essentially worldwide, you don't find any HPC system which in one way or another really not can be accessed via SSH. And then once you are logged into the system, you really need Unix skills usually to really get around, create directories, edit files, moving files, and so on. So in a way, it's not really a topic of high performance computing. These aspects are usually taught in other university courses, for instance, like operating systems. And as such, we just have here one practical lecture as a really warm-up lecture to show you a little bit already how you basically will operate the HPC systems when you come to the assignments. But before we go on the topic of this lecture today, let us a little bit look back what we learned the last time when we had our prologue of the course, which really introduced high performance computing from different points of view. Firstly, we looked a little bit on the course motivation, and we have said that high performance computing is really a field of constant change. As you remember, all the different HPC systems, how quickly they increase in the number of cores given the multi-core era. You remember that we also then added GPUs, which are many core systems, and accelerators, which are more recently added also to high performance computing. And even within this many core systems and GPUs, even some of you may have heard that we have different architectures. In NVIDIA's cards really moved from Kepler over to Pascal, and from Pascal we had then Volta and so forth. So you see also that within one part of the technology, there are even massive changes over time. And the same goes for the number of cores, the same goes for the number of memory and so forth. Hence this course, again, when you look a little bit on this picture that I provided here in the beginning, can really just do this red core, so really the basic knowledge that you have in HPC. Then when you are becoming an expert in the field of HPC, you will see it's a very broad topic. There are overlaps to cloud computing, there are overlaps to other fields of computing like quantum computing more recently. But of course, all of those in HPC, these technology changes on the one hand that we basically have for innovating new HPC clusters are driven by the needs of scientific applications and engineering applications mostly. Today we talked about the topic of co-design, which means to really co-design essentially these systems by certain applications. As a consequence, this course and its motivation is also introducing a couple of these domain-specific science and engineering aspects. Let it be crash simulations of cars, fluid and liquid flow around cars, or airflow around cars. We had already in the prologue lecture a little bit about the smoke and the adaptive mesh refinements, which is another problem. And all of these computations behind these simulations are really requiring high performance computing. Of course, there are much more complicated ones where you would even say, as we learned the last time, you may be not interested in just running one simulation. Like here, you have essentially a subsurface water flow. You would be interested in the whole water cycle. So you would have to have the subsurface simulated with path flow that we will have in later lectures. Then you would also simulate at the same time the land surface model in simulation, and then also an atmospheric model here, Cosmo as an example. We come basically in each of the different lectures back to these problems. We have here computational fluid dynamics problems, finite elemente partly. We have here terrestrial systems with completely different problems in a way, but all of them in common share the main aspect that they usually have some kind of physical laws that govern the scientific simulation. So, and these physical laws are, let's say, often approximated and by using really numerical methods that we also will have in the course to understand it better. All of these terms, of course, don't really mean anything partly to you. We will see how that materializes through the course. But of course, think about that these domain-specific science and engineering applications can be also the weather forecast that we basically know from our daily look at the apps today, but also at the news channels when they do weather predictions. And we will have in one lecture a little bit of view behind how that actually works. Then we come essentially here to the point that we have really a situation where we have interesting simulations happening. So to also give you a little bit more essentially in terms of these domain-specific applications, we have to have a broader view, because HPC these days is also used by more data science problems. You see here, for instance, a deep learning network. A deep learning network needs and requires a lot of computations for the training processes of data for the machine learning process. Also, this is something what we will learn a little bit in this course here, with an emphasis on HPC, in particular also with GPUs, which are very well suited for training deep learning networks today, also when you want to do it at scale. So scalability will be a word which is also very important in this course. So we don't want to use perhaps just one GPU that you see a little bit explained here. So GPU with device memory and connected to a host CPU with main memory access, and many different cores which are not very much powerful. Let's say the moderate number of cores, a moderate processing power of these cores, but let's say a relatively high number compared to the multi-core. So, but what we want in scalability then in HPC is just not using one GPU. We want to use maybe 96 GPUs in order to solve a complex domain-specific problems, like in remote sensing that we will basically explore later in this course. And this, in the end, is then a little bit different. It's not governed by physical processes. Still, there's lots of mathematical aspects and computations that really require then these machines. What we also learned is that HPC can be really often defined in a way that it is usually done by having every single one of these cores really massively interconnected. Because usually what you have in these physical simulations, take the weather forecast, you will always see that if you do it in parallel, you chop down these areas into different parallel regions, you would see that all of these parallel regions, of course, have to interact somehow. The region on the left or on the right, on the top, on the bottom, or in the car, in the front, in the left, in the right, say they are somehow connected. So they have to exchange lots of parameters. Take the water that we discussed in the first prologue lecture, where we said when we want to have the waves essentially that are at a current, let's say, position at the ocean, we need to know what's happening on the left, on the right, on the top, on the bottom, etc. So the surroundings here play an important, incredible part to basically compute the processes that are happening right now. And with this, we really require a lot of interactions. And with this, we really need a very good network between them. And this is really something which is very specific for high performance computing in order to really do large scale simulations. Like, for instance, you see here the example that gave rise to our logo of the course, having an airplane flying in the computer, really simulating turbulence, the stress on the materials here, which is commonly used actually for aircraft design. And then we learned also we can always differentiate a little bit maybe high performance computing by contrasted to high throughput computing. High throughput computing is much more that these single cores are there and they're usually just interconnected by typical Ethernet. So these interconnections are not so much important. So we're talking about throughput more than really interactions of different, kind of processes. Here we could say that if you want to have the maximum the word count of words within different documents, let's say 1 million documents, you can count each of the occurrence of the words separately, and you don't care about the other documents. You don't have to interact and exchanges. The only one is that you can do this at the very end, where you take then the sum of how many documents had, for instance, the word sports, etc. inside. So this is something which requires not directly an interconnect between all the cores. And with this is also much more relevant in the clouds usually. And hence our cloud computing and big data course, a complementary course we have usually in fall, is also talking much more about these problems. We moved on then and talked a little bit about the course organization, much more content. And of course, I don't want to repeat the whole content of the course. You will see now it will come lecture after lecture. However, you will be having kind of three key ingredients which you really will understand coming out of this course. And this is, of course, the idea how you program in parallel. And this is commonly done in many ways with shared memory. We said already that OpenMP will be a language you will learn, a standard really from HPC. That is, something which enables you to have basically a form of communication between different threads, but they're using memory for it. So there's no direct message exchanges, if you want, between these different threads. Instead, they actually put, let's say, their variables or whatever it is, what they just use, into memory to be picked up by another parallel thread. Now, when you think about MPI, message passing interface, and distributed memory, we learned last time that it's a little bit different, right? So we have different processes, they have their own memory, and I just cannot access the memory from the other processor here. So what's happening is I need to do message exchanges to give the content of variables or to receive the content of variables. So this means lots of message exchanges, hence explaining a little bit also how basically these physical applications inherently work. They use MPI a lot in order then to actually also have this network, this hardware network really exploited in terms of performance by really having many, many message exchanges. More recently, and what we will also see in the course content, GPUs play more and more a role in the last, let's say, 5 to 10 years. And this is really now that many libraries in scientific environments and engineering environments are ported from a normal CPU basically to GPU versions. And we will learn also in GPUs in this lecture about it and what the basic idea is of GPUs. You see it here just roughly explained. Of course, there's several other parts to it. We will learn how the process is that, data needs to be first going to the main CPU memory, and then you have to upload it to the device memory, and then actually the device, the GPU, can work on it on a very, let's say, throughput manner again, and then brings the result back to the main memory. All of this will be another lecture, and then we will see that subsequent lectures, like for instance, the deep learning lecture, will also then show you how we basically take part of this GPUs. So this was a little bit a more elaborate summary of the prologue, but let us go now in the content of the course today. So this is really more an additional lecture, really a practical lecture to show you a little bit the modus operandi, how to log in into the HPC system, how to use the HPC system, and with skills essentially, which I usually tell and basically teach elsewhere, right? Which means an operating system course or so. So we will basically start a little bit with Unix and basically the idea of having several commands. Of course, we will put this in the context of different HPC systems. So we will come a little bit back to deepest, to the modular supercomputing architecture, and just will go through the different systems which are really relevant for this course, the deep test cluster and also the Jotun HPC cluster that we have at the University of Iceland for teaching. I will then demonstrate just a couple of Unix commands, really. If you see on the web these days, you can get all of the Unix commands very well explained. So there's no point of repeating all of this. One highlight, however, in this today will be the module environment, which is also a very important part in HPC today. So lots of application libraries are basically often available on HPC machines via this module library, and we have a look. Then I will introduce you to the basic editor VI that basically all the HPC systems kind of offer. My students in the past, however, used also sometimes Nano, sometimes Emacs. So I will not say what editor you really need to do and have to use here for the assignments in the course, but we need an editor. And I will show you just the kind of minimum editor, which is the VI, shortly by giving you some demonstrations. Then in the second part of the course, we will look a little bit behind the scene of thinking about how we connect to these systems. So how we connect actually to HPC systems. There are several different ways to do this. One is, for instance, using the secure shell. an SSH protocol, really, from a client-server architecture to access the systems. And there are different ways of doing it. You could have an SSH key, a private public key pair, prepared basically in order to access these systems, which I will demonstrate with a deep test cluster. Or you basically can use SSH, the protocol, without an SSH key, really, but rather use the username password function that we will then explain a little bit with the HPC system Utin. With Utin, however, it's also very important to understand that there needs to be a workaround for an external login. If you're working from home, we have COVID-19 times, so this means some of you don't have the how EVPN. However, with the how EVPN, it would be easier. But if you're external, let's say you maybe do some assignments out of your company environment or wherever you are, there's a kind of workaround to really go first to Heckler and then to Utin that I will shortly describe. So again, it's really a lecture which is more or less supportive, but take away the message that with this lecture, you're really capable of using quite a lot of high performance clusters, which are actually out there in the fields, and use them for different purposes, whatever it is, what you want to do. And in a way, the module environment is already pointing to a HPC environment tool that is really necessary these days to understand, to work with. Hence, we will come back in the assignments about it and also in the different lectures. Now, when we come back to understanding HPC systems, we had this already in the last lecture. This time I brought you more an understanding video here from the DEEP project, which I already explained the last time, which shows you a little bit again an emphasis on HPC, really from a, let's say, starter point of view, because we're at the beginning of the course. You know, we have sometimes sound issues, but you see always under these references, you will also find the videos usually. Okay, so let's come back to the lecture. You have seen a small introductory video. I hope the sound was this time working by embedding it here in the slides. This is of course something related to Zoom here. If it doesn't work, then please follow the link. And in the link on the website on the top, you will see then basically a hint where the video can be found. So with this, we have already understood essentially these different concepts around basically HPC, but also have understand that exaflop is now something which really means these computations there that you see really by having 10 to the 18 floating point operations per second. So you can imagine, as also explained in the video, hey, performance computing means it can do lots of computations and it can do it very fast and very many of those. And of course, this is a, let's say, competition. In a way, it's a friendly competition. Of course, many countries, as was alluded to the video, are now going towards this exascale performance. What you see here is, however, not the exascale era. It actually was a petascale era, if you want. And also there was a technology race, if you want. And the point that I want to make here is coming back to our course lecture today is really that however you go back, my starting systems is a jump system in Jülich, essentially, or you use here Eugene, which was an interesting technology at that time. So you see, essentially, whatever technology changes and you see the environment around it. So there's a second floor. Sometimes there's liquid cooling these days. At that point, it was just more air cooling, maybe. So this is our technology changes, but there's one denominator that you could say in all the time, it was always accessible via SSH. And mostly these systems are also operated via Unix command. And this is really valid until today. Even if you go to the newest supercomputers, we still use SSH and Unix, and hence it is worth to have a small practical lecture around it. And basically, we need also real systems. So we will have two systems in the class. The deep projects is one that I already alluded to the last time, where we said, okay, this is a system around modular supercomputing. We co-design it by different applications, if you remember. The University of Iceland is also there involved and actually contributes to the co-design with deep learning, machine learning in the field of remote sensing and earth sciences. So this means really an intensive collaboration with vendors in the field. So we will see that we have vendors like Macware, where we have a real cluster we can access in the course, a deep test cluster, which we're going to use for several parts of the assignments. However, we have also in Iceland, of course, a system that we're going to use. So the deep test cluster that we have is basically a really modular supercomputer. There are different modules around it. If you remember from the last lecture, the prologue was already alluding a little bit to the cluster module. And then we have an extreme scale booster module that is available already, but we use mostly in the course a data analytics module with some GPUs in order to get this. This is a reason because GPUs usually are quite expensive. You cannot just go to the market basically somewhere, even on Azure or on cloud systems today, and get lots of GPUs for free. So that's not happening. In Google Colab, this is happening a little bit there. Every now and then you get some GPUs, but they're also different architectures. So you cannot really choose which architectures you really get. So in this, we are grateful to have the opportunity to really use a deep test cluster for some parts of our assignments so that you can really get hands-on on GPUs in a HPC environment. We use here the NVIDIA, basically V100 GPU. There's actually now also a more successor of this GPU. We will talk in one of the GPU lectures about it, but essentially it keeps the essence of using GPUs. So this was a deep test cluster. Then the Jötun cluster that we have here in the Icelandic National Competence Center available for teaching is another machine we're going to use. You have here the website eHPC, basically under this link where we basically are already in the moment creating a website which is really reflecting also the community that is here in Iceland. So we will actually really increase the presence of the website. But in the moment already, what you can see is the two HPC machines which are operated here. You can go to this webpage and see Jötun, of course, which is our test cluster. but you also can use, of course, then GAPÖ if you are, let's say, more, becoming an expert more and more in HPC and really know what you're doing in terms of your parallel application. You can also basically aim to get some time on GAPÖ. And so the idea is really to learn different systems, but when you go through these different systems, it's not really like a Windows and Mac machine or something like this. It's really, in a way, complete different architectures underneath, but they're operated in a very similar way. We will see scheduling of HPC jobs in the next practical lecture. We will see Unix is there. We see that we can access it with SSH. So, and many of those these days offer the module environment. So these are the ideas of the course, so that you can really hop between different HPC systems. And that's what researchers do these days, really. And in a way, I would really do now a little bit of demonstration. Always, you see here on the slides, I still have the same aspects basically covered. So let's go a little bit here to the practical stuff. Here's an SSH client, and I don't go now in the details of saying how I configured it. I just use one pre-configured one in order to really concentrate first here on the Unix environment. And then in the second part of the course, I will go much more deeply. What is actually the idea behind these, and what is now the idea how you can create such a connection and so forth. So this was now using the SSH client, MobaXterm. I will also come in the second part behind it. But let us now look a little bit what Unix really entails. And in a way, you can see here a welcome screen that says we are correctly logged in on the deep test cluster. But if you want to test it, for instance, there's one of the important commands that you should know, which is always hostname -r. So this shows you really a complete host name. You see also that this system we basically collected to seems to be named like this, although we say it's a deep system, so it had an alias that we used. And here you directly know on which system you are. So you're not anymore on your laptop. It looks like this, essentially, because you have here now, of course, the whole system, right? And the kind of still operated on your own client or on your own laptop. But of course, what we do here is now we have a remote display, which is then basically forwarded through this SSH connection. We're really on the server, as you see with hostname -a, which means, in other words, also, when you go now a little bit further, and we could do, of course, the same thing later on in Newton, I will demonstrate. You will then see that, of course, this means you should be also maybe a different user. And this is something what you can find out with who am I. But of course, you will also understand that, of course, then the files are changing. You're not anymore on your laptop. You're now remotely on a cluster. The cluster has a file system. Sometimes they have parallel file systems, very powerful. We'll also talk in this lecture series about it. But you don't find your files anymore. And let me just demonstrate this again. That means that you have several commands, like for instance, ls-al, that you can use to explore really the system and the file system on the other side, right, on this test cluster. So let me demonstrate this a little bit here with a couple of commands, really. So you see here a very nice representation, basically in MobaXterm, which is much more towards a kind of browser setting or a Windows Explorer if you want. Of course, you could use this, and you see already what's happening here. So we have apparently an HPC course fall 2019. We have already a basically a directory here, but this is not really how you would use Unix usually, right? I mean, you could use it here in the MobaXterm, but it's also good to know a few couple of commands that you can use here. And when you're here in this command line over here, you can do, for instance, who am I? This is not surprising. We used the Riedel one here as an example of a user account really to connect to the system. So that's who I am. But I also told you we can use ls-al, for instance. And when you do this, you see there are lots of data already there. Of course, this is not a surprise for you. We told already the course is basically based on a long tradition. So HPC directories, HPC course fall, which was our last one. We changed the setup now and putting the HPC course into spring semester. And you see also apparently some course MLDL parts. And now, as these are directories, you can do different things with it. One thing is important, like the cd command. You can go to the HPC course. Maybe let's take the one that I already created, Spring 2021. We can look, and what we see is essentially not much. So we can maybe create a directory and say mkdir. What we say is first or assignment 1, just to demonstrate here the mkdir, which really creates a folder, creates a directory. So when you do now ls-l, then you really find that here's a directory, and you always basically see that here on the D in front, which stands for directory, and here the usage rights basically for different parts, where we'll also come back to in the assignment. Then what you can also do is, of course, go back. You see cd point is, for instance, a very important one where you go up in the folder hierarchy. I do it on purpose a little bit slower for those which really had never Unix interaction. And in previous courses, or basically previous years, I countered this, that this is actually happening much more as smartphones are more and more used, iPads are used. People lose the connection to file systems. They are not really aware how to go between different folders. They're just switching between different apps. And people lose a little bit the idea sometimes of folders in that. Also, of course, the use of these kind of Unix commands gets more and more rare. People are really used to these kind of nice, flashy browsers. So not really go like, let's say, in the very old times when you had Windows just beginning or MS-DOS and old operating systems, where just this was the only way how you interact essentially with these systems. Now, when we look on ls-l, we see now there are also different courses. Let's go a little bit and explore, of course, one from spring, fall, for instance, from the last time, right? So you see here, this is rich. There's already much more, apparently. So what is the HPC part? We're curious. Okay, there's not much in it. Perfect. So you see we can move throughout this directories in different manners. We can see here the 2019 HPC course MLDL parts. This is much more richer. There's much more. And this is also not surprising because these are now deep learning scripts and deep learning Python scripts we will allude to then when we come to it in the assignments and also part in our lectures. And of course, that's why we wanted to use a test cluster, right? On the deep, we wanted to exploit the GPUs here with deep learning. So that's why we find here lots of these scripts from the last course. Now, let's go back a little bit to our own course we have now, which is apparently very empty, which is, of course, clear. We have just our first practical lecture here. Just to demonstrate you a little bit the VI, this editor, as I said. And while I'm speaking here, it's important to notice that essentially I put here everything on the slides I'm talking to. I didn't demonstrate yet the PWD, the power. It shows you just the folder you're actually there, the print working directory. And then all the things I just did with mkdir as examples, you see also here a little bit explained. But really, if you are in doubt, don't hesitate. Go to the web. You will find Unix, mkdir, for instance, as a search string. You will find lots of information that really helps you to understand it, and cd as well. And as you use them again and again, these commands really get more into your head. So at the end of the course, you're really laughing at this and would say, I have used that now so many months, I really know what it is. Now, the HPC system module is something I come back to in a minute. Let's just look a little bit on this idea of really using the basic editor VI, or we can do it already now. We say this module avail. It shows you essentially here all the different applications and libraries and tools which are available at the system. So these modules can be loaded with module load or used in a job script that we will see also when we essentially have our assignments, and have much more the way how you submit an MPI job when we start essentially already with some scripts in the next practical lecture that is more explaining how you really submit to an HPC cluster using a Slurm scheduler. But for today, this is just an appetizer of this. You see that essentially there are different file formats, HDF5, there are different versions of Python available here, which you can load. You see there's even R available, which is a statistical software. You see SkyKit is for machine learning, data mining. You have TensorFlow, which is, for instance, a version here for GPUs on Python, which really enables deep learning, the same like PyTorch. It's also another deep learning library. And all of those can be actually really loaded then by doing, let's say, module load. And then we can use Python here, for instance, 3.6.8. We do here the versioning because we usually have this 2.7.16 also for some reasoning of going back. And then you essentially can use Python and using it for your problems. So, but this is really, let's say, just the beginning. We will have this, of course, much more interesting when we then look at concrete MPI libraries we're gonna load, and also maybe CUDA libraries we want to load in order to do this. But of course, now you don't really know what that is. You don't have the knowledge of MPI yet, so we will come back to this, of course, after we have explored what the message passing interface really entails, or what CUDA means in the context of GPUs. So this is essentially how you then load software and use it. If you want to create files or work with files, I told to use, there's different editors around. You could use Nano, you can use Emacs. I use often basically just CVI because it's basically everywhere available. You see here an example that I already created. Welcome to our HPC course in spring. I can, with a double D, for instance, delete the lines. With the escape button, you always come into a sort of command mode where you then with colon, for instance, A can append, and then you can write text again down there, or you basically can put colon E for insert. There are different ways how you can really operate this, and of course it gets more realistic and more usable when you really try it in practice, right? So hello and welcome to our HPC course in spring 2021. So, and then you come with the escape again to the save, or basically to the command mode, and then with colon write. And I also do quit here, and then this one, we really can go out of this. And of course, this has lots of different commands that you can basically find out. There's a yank command to copy paste. But again, I also don't want to really show you how editor works. It's not the part of HPC here. Pick the editor you want, and then you basically see the options that are basically most comfortable to you. Of course, you can remove files. So rm test file here has now removed this file we just created. Of course, if it's not there yet, we can recreate it with VI. We can do what we just said, a new file. And then we'll talk about something and do it, write and quit it. And then with ls-il, you see the file has been created. And we can also essentially then just remove it again, rename it. This one idea, you can move files from test file to test file 2. And then suddenly you see it's named as test file 2. So another magic of Unix really, but not really. It's just interacting with files as you would know from also browser-based variants, or also on your Windows Explorer. Right, so with this, I think we have covered a lot of basics for Unix. And you can imagine I can now go on and go to much more commands. Important is that you realize this HPC system module environment that we had. This is important also later for our compiling, right? When we have our first ping pong and hello world programs together, you will see that this is already there. Important to learn which modules you have to load in terms to get the right compilers. We will talk about this. And you have now learned what it's about with the module availability and also the loading. That was essentially on this slide, so I don't need to repeat them. We have done the MPI editor here and basically just created a file. We have seen removing a file is possible with RM. We have seen it's also possible to move a file to another file name. And I think with this, I'm really stopping here with the first part, really referring to the web. If there's much more about Unix you want to know, please go to the website or use basically Google to find more information about it. Of course, I'm also there for assignments or in Q&A sessions if you need me and have some questions about some of the Unix commands. Of course, we can clarify it there as well. So that's all for the first part of this lecture. Let's come back to this lecture after a short break in the second part of this lecture.